So have you ever come home from a long plane ride only to open your suitcase to find your shampoo and toothpaste explode all over your clothes? That's happened to me a few times, and I kind of wanted to know why. And the reason is due to Boyle's Law. Boyle's Law was discovered by Robert Boyle, coincidentally, in the 1600s. He was in Ireland. He did some chemistry back then. And he discovered that the volume of a given amount of gas held at a constant temperature varies inversely with the pressure. All right, so what does that mean? Let's look at this picture and this actually helps us describe that. All right, so let's say I have a canister of gas, 10 liters of gas inside, and I have a pressure of 1 atmosphere on there. If I take my constant, multiply pressure times the volume, I find that we have a constant of 10 atmosphere liters. Okay, fair enough. Let's say I push down on that canister. I push down on it with twice as much pressure, so now my pressure is 2 atmospheres. What's going to happen to the volume? Well, you guessed it, it's going to half. So there is a relationship between the pressure and the volume of the container, as long as the temperature is constant. So if we were to multiply these, we get the same thing as we did before, 10 atmosphere liters. So notice that P1 V1 equals P2 V2. These two sides are the same. Great. Okay, so let's go over here. The relationship between the pressure and volume, what is that? Well, we noticed that as pressure goes up, so does the volume goes down. They have an inverse relationship to each other. And also, pressure goes down, volume will then go up. They're completely inverse of each other. So how do we graph that? Well, if we have volume on the y-axis and pressure on the x-axis, it will have a graph, and we would graph all our points, it would have a graph that looks similar to this. Notice that the volume will never reach 0, and the pressure will never reach 0. That is because you'll never have a volume that's nothing, and you'll never have a pressure that's nothing. So we can have a curved graph that looks similar to this. Notice it's also a negative slope because our relationship is inverse. All right, if we were to mathematically look at Boyle's Law, let's reiterate the fact that pressure 1 times volume 1 equals the pressure 2 times volume 2, as we demonstrated earlier. That's our mathematical relationship. Okay, so let's actually put this into practice. Let's say you have a sample of neon gas that occupies 0.22 liters at 0.86 atmospheres. What will be its new volume at 29.2 kilopascals? Well, the first thing you should notice is that when we're dealing with pressure, we want to make sure that pressure is always in the same unit. In this case, pressure is in atmospheres in the first scenario, and the second one is in kilopascals. I don't like that, so I'm going to put them in the same unit. I'm going to just randomly choose atmospheres. It doesn't matter if you choose atmospheres or kilopascals. It'll give you the same answer. But I like atmospheres. So I know that 1 atmosphere equals 101.3 kilopascals. Okay? So I'm going to change 29.2 kilopascals to atmospheres. So I know that 101.3 kilopascals equals 1 atmosphere. So 29.2 divided by 101.3 gives me 0.288 atmospheres. Okay, so let's start out with this. So instead of using this number, I'm going to use this number. So sample of neon gas occupies, this is my V1, and this is my P1. So 0.860 atmospheres times 0.220 liters equals, we went to our new volume, and our second pressure is 0.288 atmospheres, and we don't know our new volume. That's what we're looking for. Now, before we even solve this, let's predict what our volume should be. Our atmosphere actually goes from 0.8 down to 0.2 or 0.3, so it drops. So what's going to happen to our volume? Our volume should increase according to our relationship that we discovered earlier. So let's see if that happens. 0.86 times 0.22 will give me, hold on, I don't know that off the top of my head, 0.86 times 0.22 gives me 0.1892 equals 0.288 Z2. We're going to divide by 0.288, divide by 0.288, and we get 0.66 a rounding liters. Our second volume is 0.66. So that match it. Volume was 0.220, now it's 0.66. It did go up, which is what we predicted. So we just proved Boyle's Law. All right, one of the gas laws that you might come across is called Charles' Law. And Charles' Law was formed by Jacques Charles in France in the 1800s. And he discovered that the volume of a given mass of a gas is directly proportional to its Kelvin temperature at constant pressure. There are two things that you want to make sure you know, or you notice when you're reading this gas law. One is Kelvin temperature. We want to make sure our temperature is always, always, always in Kelvin, or else you're going to get the wrong answer when dealing with this Charles law. And you also want to notice that it's a constant pressure. So two variables that are changing is volume and temperature. Okay, those are the two variables you're dealing with. So let's say we have two canisters. Notice they're at the same pressure. So in this canister, we have gas pressure, normal temperature and pressure, and then we actually heat it up. Okay, so now we're increasing the kinetic energy. Those gas particles are now moving at a faster rate, and they're able, if we want to make sure the pressure is constant, they're actually going to push against this, the top of this thing and actually move, like, making the volume larger. So if you notice, the relationship between temperature and volume, as we increase temperature, we also increase the volume as long as pressure is constant. Okay? So Charles' law, its relationship is, we have a direct relationship as stated in the actual law, and we can actually make it mathematically equal. Volume 1 divided by the temperature of 1 equals the volume of the second one divided by the temperature of the second scenario. So this is actually Charles' law mathematically. If we were to make a graph, the graph of Charles' law, is at 0 Kelvin, we're going to have 0 volume, because at 0 Kelvin, nothing moves, and the volume of a gas is actually going to be 0. And it increases as the other one increases also. So you're going to have a linear relationship that looks like this. As temperature increases, so does the volume of the gas. It also increases. Also, as temperature decreases, the volume of the gas actually decreases. So let's actually do a demonstration that shows this. Okay. So over here I have a candle floating in some water. I'm going to light that candle. I'm going to actually put my safety glasses on first. And so let's do that. Okay. All right, I'm going to put this in here just to be safe. Make sure I don't burn anything down. Okay, so what's happening, the air particles around this candle are actually heating up. Okay, so they're expanding. I'm going to capture this, I'm going to put this glass on top of this candle, and what that's going to do is it's going to end up going out, because it's going to, all the oxygen in this glass container is going to go away. It's going to be used up. So as it's being used up, the candle is going to go out. And notice when it went out, a lot of the volume in the water level rose inside the canister. Now, why did that happen? Because when the candle went out, the temperature of the gas particles inside this glass chamber actually dropped. And that made the gas particles actually have a lower volume. Because the gas particles had a lower volume, that volume had to be replaced by something. And it was replaced by the water at the bottom. So the water was actually able to be sucked in to the glass container to replace that volume that was then lost due to the drop in temperature. Okay, so let's do a problem that you might see in class. Okay, something that you might see in class. I'm going to take off my goggles. Don't need them anymore. A gas at 40 degrees Celsius occupies a volume at 2.32 liters. If the temperature is raised to 75 degrees Celsius, what will the new volume be if the pressure is constant? So I'm dealing with temperature and volume. So I know in my head that's Charles' law. Charles' law deals with temperature and volume. Okay, it also deals with temperature in Kelvin. So I want to make sure I change these temperatures to Kelvin. So knowing that my formula is V1 over T1 equals V2 over T2, the first volume that we're going to deal with is 2.32 liters. The first temperature is 40 degrees Celsius. We add 273 to that, and we get 313 Kelvin. And then our second volume is, we don't know. That's what we're looking for. Our second temperature is, I'm going to turn this on real quick. Our second temperature is 75 degrees Celsius. We're going to add 273 to that. And we get to 348 Kelvin. We cross multiply 348 times 232 divided by 313. We get our new volume, which is 2.58 liters. And let's see if that makes sense, okay? So we increased the temperature. We went from 313 to 348. What's going to happen to volume? It should also increase, which it did. 2.32 increased to now 2.58 liters. So mathematically, this is correct. So hopefully all this, the demonstration, the graphs, and the problem helped you understand that how Charles' law works. All right, so one of the gas laws you'll see in class is going to be Gay-Lussac's law. And Gay-Lussic actually described the relationship between pressure and temperature when the volume remained constant. So let's actually look at this ourselves. So we have a container here, and it's a 5-liter container, and inside has gas particles. Okay, so it's at room temperature, and the gas particles are hitting it at some sort of pressure. And that's fine. Let's say we heat it up, so we're increasing the temperature, and the kinetic energy of the particles within the 5-liter container is increasing as well. And they're hitting the sides of the container at high speeds. And so what's going to happen, as long as the volume remains constant, which it is, the pressure inside the container is going to increase dramatically depending on how much the temperature is increasing. So let's talk about this relationship. We know it's a direct relationship. As temperature increases, so does pressure. And conversely, as temperature decreases, so does pressure. So temperature and pressure have a good relationship as long as the volume remains constant. Okay, so let's put this in mathematical formula. Pressure 1 over temperature 1 equals the pressure 2 over temperature 2. Because this is a direct relationship, they are divided by each other. The temperature, we're going to make sure is in Kelvin. And the reason we make sure it's in Kelvin is because we want to make sure that there's no negative numbers on the denominator. And Kelvin's the only temperature scale that actually only has positive numbers. So we're going to make sure this is in Kelvin. And this is Gay-Lussac's law mathematically. Graphically, if we put temperature on the x-axis and pressure on the y-axis, we know that as we increase temperature, we also will increase pressure, creating a positive slope. Okay, let's actually look at this in a demonstration. So what I have right here, I'm going to put my goggles on, make sure we are safe. Safety comes first. We have, what I'm having on this hot plate is a Coke can, as you can see, and I'm heating it up. So the gas particles inside the container are heating up also, and they're hitting the pressure of a soda can at high speeds. But it actually is open, so it has a place to escape, so the pressure inside the container is equal to the pressure outside here, and so everything's all good. But what I'm going to do is I'm going to be flipping the can over into this ice water bath, sealing the container. And what's going to happen is the temperature is going to drop, and so the pressure inside the container is also going to drop. But the pressure outside is going to remain the same. So what is going to happen? Let's see. Whew. So, as you can see, it actually didn't take much at all. What happened was the pressure outside was so much greater than the pressure inside because we had dropped the temperature so dramatically that it actually pushed on the can and crushed it, as you can see, completely crushed it. Okay. Don't try that at home. All right, let's turn this off. And let's go and solve a problem together. Okay, so if the pressure in a car tire is 1.88 atmosphere, there's our first pressure. At 25 degrees Celsius, there's our first temperature. What will be the pressure if the temperature warms up to 37 degrees Celsius? Okay, so first I want to make sure these temperatures are in Kelvin, not in Celsius. So I'm going to change them. 25 degrees Celsius plus 273 is equal to 298 Kelvin. 37 degrees Celsius, that should be a degree Celsius, plus 273 is equal to 310 Kelvin. Okay, so my first pressure, and when I woke up, I put the tire pressure was 1.88 atmospheres. And the temperature outside was 298 Kelvin. We don't know, we went into the pressure at the end of the day when it's 37 degrees Celsius. We don't know it, so we're going to say X over 310 Kelvin. We cross multiply 1.88 times 310 divided by 298, and it's going to give me 1.96 atmospheres. So the pressure inside the tire is actually going to increase as expected because temperature also increased. So this is an example of Gay-Lussac's law in an everyday application.